Hello and welcome to our oral presentation of Lab 4, the ranking cycle. Before we can perform our experiment, walk you through the data we pulled from the simulation, and conduct our findings, we need to get set up. While that's heating up, let's do a quick recap on what actually happens in the Rankine cycle. The cycle begins when high-pressure liquid comes out from the pump and goes to the boiler. The boiler turns that liquid into a high-energy vapor. The vapor expands through the turbine and outputs shaft work as well as low-energy vapor. The vapor then travels to the condenser to turn back into a liquid. This low-pressure liquid is recycled back to the pump and the process continues. In our experiment, we do not have water being recycled. In this situation, we are assuming the pump and the turbine have no heat transfer. The boiler and condenser are assuming no pressure drops, but they do have heat transfer. The system has work coming in at the pump and work coming out at the turbine shaft. The system also has heat coming in at the boiler and heat leaving at the condenser.
Perfect timing. Our system pressure just hit 820 kPa, which means we need to start to slowly open up our steam valve. The meter here is showing a nice reading of 789 kPa as the pressure begins to drop. To ensure our computer is getting the right data, we can compare these current and voltage meters to the ones on our system. Everything is checking out fine for this point in time as both sets of meters are reading roughly 0.3 amps and 3.8 volts. We know things are operating well when steam begins to release from the condenser. And better yet, we've got power. Well, we are out of water and we're going to start to purge the system. We got to fully open the steam valve and turn the rheostat knob all the way to 100. A quick measure of how much water drained from our condenser, and we'll use this later to find our mass flow rate. Can't forget to save our data log and open it up with Excel so we can further analyze.
After looking at our spreadsheet with over 1900 seconds of recorded data, we divided our sheet up into 27 minutes of readings. Just like Grayson discussed in his Rankine cycle overview, as steam starts to enter the turbine, it quickly jumps in rotations per minute and backs off towards the end of the cycle. Using both the pressure and temperatures that were recorded by the software, as well as the saturated water and superheated vapor tables, we were able to interpolate the enthalpy and entropy values for the turbine inlet and outlet. This process was again repeated to determine our boiler enthalpy and entropy values. Full transparency, the data we pulled was from our second trial run of the Rankine cycle lab. To be honest though, would this really be the Rankine cycle lab if we didn't have to run it twice? Due to our system having a pressure surge on day one, we were unable to obtain enough quality data because our water levels ran out so quickly. So we had to actually come in a second time on that Friday to complete it. And on the second trial, we actually experienced a pressure surge again, but we realized this was just due to a faulty sensor. Seeing that our pressure gauge actually was reading us useful numbers, we continued the lab and were able to finish successfully. Working through these technical difficulties, we were able to obtain about 13 minutes of quality data for our lab. This is what we called our sweet spot, the green, if you will, on our spreadsheets. This is important to note, though, because we want to calculate our thermal efficiencies based on true enthalpy at the certain points in time that we did. Highlighted in green is what we're going to call our sweet spot zone. As temperature and or pressure increase or decrease, enthalpy and entropy follow the same trend. This section of data shows slight fluctuation, but an overall trend of decreased enthalpy at the turbine outlet compared to the turbine inlet, as well as a decreased entropy at the turbine outlet in relation to the inlet. This trend carries over to our boiler table as well. As the temperature and pressure drops within the boiler, the enthalpy and entropy values do the same.
Here are those trends of pressure and temperature shown in the figure as a function of time. Temperature at the turbine inlet shows a nonlinear decrease as it drops from roughly 109 degrees Celsius to 105 degrees Celsius, while the outlet temperature decreases from 97 degrees Celsius to 95 degrees Celsius. Pressure also reads a slight decrease, starting at 139 kPa to 127 kPa at the inlet, and a drop of about 100 kPa as the steam travels through the turbine, bringing it down to about 39 to 33 kPa at the outlet. The boiler temperature has a little flutter over time, but tends to actually drop roughly 1 degree from 172.4 to 171.4 degrees Celsius. Pressure shows more change as it decreases from 737 kPa to 716 kPa.
So let's talk about efficiency. Thermal efficiency is the measure of work out of a system compared to the work necessary to be put into the system. The formula looks like this. NTH equals 1 minus Q out over Q in. In our case, the system provided us with the data on how much power we were getting, typically around 1.2 watts. This is roughly enough to charge a phone. To find our thermal efficiency, we then needed to calculate the mechanical power, which is represented by this equation. P mechanical equals m dot times enthalpy in minus enthalpy out. Using the 1,000 milliliters of water we collected in our beaker out of the condenser and 27 minutes of flow, we concluded a mass flow rate of 0.0006172 kilograms per second. Used in combination with the interpolated inlet and outlet enthalpies of the turbine, we found our mechanical powers for the timestamps. These averaged around 0.3 watts. Each thermal efficiency was calculated using these powers in this equation. Second law efficiency is needed because the first law efficiencies fail to take into account an idealized version of the system for comparison. To calculate the second law efficiency, we use this equation. Revolution efficiency, in our case, was given, with TL being 293 Kelvin and TH being 473 Kelvin. This was then plugged back into our second law efficiency equation with the calculated thermal efficiencies to get our second law efficiencies at each timestamp as well. All of these efficiencies are translated into this table and worked out perfectly in our sweet spot with the typical thermal efficiency of 64 to 69%, but second law efficiencies of closer to 24 to 26%.
Here again is that mass flow rate we use in our thermal efficiency equation. It is always important to conduct an uncertainty analysis on your experiment to gauge the largest error that may be reasonably expected in your results. In our case, a glycerin-filled pressure gauge resulted in an error of plus or minus 8.94 kPa.
As you can see here, the power generated from the Rankine cycle is quite low. The power from the turbine output is much larger than the power output of the generator. This loss of power is due to the shaft from the turbine to the generator. Although the power outputs are different, the power created by each component is mostly consistent over time. When comparing time versus efficiency, you can see the second law of efficiency is a much more accurate depiction of the efficiency of the cycle, because it's lower and more realistic. You can notice an increase in efficiency as time progresses with the boiler temperatures decreasing.
If we've learned anything from all our labs, it's that theoretical, experimental, and computer simulated results will always slightly differ. This is because the sources of the data between the three processes vary in their efficiency and accuracy. It is assumed that the experimental results represent the real behavior of the object under test with specific measuring errors, and that these errors are bound and lie within certain margins. On the other side, the simulation results represent the behavior of the same object based on its theoretical model. In our case, experimental is different than theoretical because the uncertainty analysis that was done on the pressure gauge resulted in plus or minus 8.94 kilopascals. The theoretical values could have been slightly skewed from the pressure gauge having that uncertainty, and the computer tabulated pressure had a faulty sensor from the start, even though we found a sweet spot with it. This all in combination with theoretical differences resulted in a variety of data sets compared to each other.